Hey there, science fans! Welcome back to the For Science Salah Lotfy channel, where we explore the latest advancements in science and technology. Let's dive into today's exciting topic. Let's talk about something we all use every day: energy. Our cities are like giant machines, and they need a constant supply of power to keep running. Think about it: traffic lights, hospitals, schools, our homes, they all need electricity. And guess what? Our need for energy is only growing. More people are living in cities than ever before. We're using more devices, from smartphones to electric cars. All of this means we need reliable energy sources to keep our cities humming. Clean energy is the way to go. We need to reduce pollution and protect our planet. That means finding ways to generate power without harming the environment. It's a big challenge, but one we can solve with innovation and smart thinking. One promising source of clean energy is nuclear power. Nuclear plants can generate a lot of electricity without producing greenhouse gases. But here's the thing: safety is absolutely crucial with nuclear power. Nuclear plants need a constant supply of electricity, even if the main power grid goes down. Why? Because they rely on electric pumps and cooling systems to keep the reactor core stable and prevent accidents. A sudden loss of power could lead to a dangerous situation. That's why nuclear plants need reliable backup power systems. These systems must kick in immediately if the main power fails, ensuring the plant remains safe and operational. So, how do we make sure nuclear power plants always have the backup power they need? The answer is hybrid systems. These systems combine different energy sources to create a super reliable backup. Think of it like having a team of superheroes with different powers. If one superhero needs help, the others are there to save the day. Hybrid systems for nuclear plants typically include a combination of traditional power sources like diesel generators and newer, cleaner technologies. These newer technologies are where things get really exciting. Let's explore some of these cutting-edge options. Section 4. Superstorage, keeping the lights on with magnets. One amazing technology is superconducting magnetic energy storage, or SMES for short. It sounds complicated, but the idea is pretty cool. SMES systems store energy in a powerful magnetic field created by electricity flowing through a special kind of coil. Imagine a giant invisible battery made of magnets. When the power grid goes down, the SMES system can release a burst of energy instantly, keeping those essential systems running. The best part? SMES systems are very efficient and can store energy for a long time without losing much power. Plus, they don't produce any emissions, making them a super eco-friendly option for backup power. Section 5. Batteries and hydrogen, powering up the future. Another dynamic duo in the world of hybrid energy systems is advanced batteries and hydrogen fuel cells. You're probably familiar with batteries from your phone or laptop. Well, imagine those batteries on a much larger scale. Advanced batteries can store huge amounts of energy from renewable sources like solar and wind power. This stored energy can then be used to provide backup power to nuclear plants during an outage. Hydrogen fuel cells are another exciting technology. They convert hydrogen gas into electricity through a chemical reaction, producing only water as a byproduct. Hydrogen can be produced from renewable sources, making it a clean and sustainable fuel source for backup power. Section 6. A hybrid future, clean energy, safe energy. As we build the cities of tomorrow, we need energy solutions that are both clean and reliable. Hybrid systems are the way to go. By combining the power of nuclear energy with cutting-edge technologies like SMEs, advanced batteries, and hydrogen fuel cells, we can create a future where our cities have the energy they need without harming our planet. It's an exciting time to be a science enthusiast. With a little ingenuity and a commitment to sustainability, we can power our world safely and responsibly for generations to come. Keep those questions coming, and never stop exploring the wonders of science. Now let's move on to today's topic, and explore the research at the heart of this episode. Today's research: automation network computer-aided design of hybrid electrical energy backup system for nuclear microgrids, was only recently released by the publisher. It comes from Associate Professor Dr. Ashraf Aboshosha, a leading researcher in the Radiation Engineering Department, Industrial Irradiation Division, at the National Center for Radiation Research and Technology, part of the Egyptian Atomic Energy Authority in Cairo, Egypt. The paper was published in the International Journal of Hydrogen Energy and has already gained attention for its innovative approach to energy solutions in nuclear microgrids. This research, submitted on June 8, 2024, revised on August 24, 2024, and accepted on September 30, 2024, tackles a critical issue in energy management: how to ensure stable and reliable backup power for nuclear facilities using hybrid systems. At the heart of the study is the development of an automation network computer-aided design, or CAD system, that integrates both renewable energy sources and traditional power backups. The CAD system allows for more efficient control and management of hybrid electrical energy backup systems, which, honestly, is essential for the sustainability and safety of nuclear microgrids. Nuclear microgrids are becoming increasingly important in today's energy landscape, especially with the rise of renewable energy. They operate semi-independently from the main power grid, which makes backup systems crucial for maintaining continuous power in case of grid failure. Dr. Aboshosha's research addresses the challenges in this area by optimizing the combination of solar, wind, and conventional energy sources, ensuring that power is consistently available even during interruptions or emergencies. In his study, Dr. Aboshosha demonstrates how this hybrid system is designed to work efficiently through a detailed simulation model. This model not only highlights the effectiveness of the system in real-world scenarios, but also outlines the steps for its practical implementation in industrial settings, particularly in nuclear power facilities where safety and reliability are paramount. The significance of this research lies in its potential to revolutionize backup energy systems in critical infrastructure. By using advanced automation and intelligent design, the system proposed by Dr. Aboshosha offers a sustainable, cost-effective solution for the future of nuclear microgrid energy management.
Our world runs on electricity. It powers our homes, our businesses, and even our safety systems. But what happens when the grid fails? This question becomes even more critical when considering nuclear power plants. These plants require a constant supply of electricity, even in emergencies. Traditional backup systems, often relying on diesel generators, have limitations. They can be slow to start and contribute to air pollution. This is where the Hybrid Electrical Energy Backup System, or HEBs, comes in, offering a revolutionary solution for nuclear safety. HEBs represents a paradigm shift in how we approach backup power for critical infrastructure, ensuring reliability and sustainability. Nuclear energy, while a powerful resource, demands the highest safety standards. A disruption in power can lead to catastrophic consequences. The need for a robust and independent power source is paramount. HEBs addresses this need head-on, providing a safety net for when the grid falters. The Hybrid Electrical Energy Backup System, or HEBs, is more than just a backup generator. It's a sophisticated microgrid designed to provide uninterrupted power to nuclear facilities. This system seamlessly integrates renewable energy sources, battery storage, and advanced automation. HEBs ensures a continuous and clean energy supply even during grid outages. Imagine a system so resilient that it anticipates potential power failures and responds proactively. That is the essence of HEBs. It's not just about keeping the lights on, it's about maintaining the critical safety systems that protect us all. This proactive approach sets HEBs apart, ensuring that nuclear facilities remain safe and operational. At the heart of HEBs lies a combination of cutting-edge technologies. Solar panels and wind turbines harness nature's power, contributing to a sustainable energy mix. Advanced battery systems store excess energy, ready to be deployed instantaneously when needed. This combination of renewable sources and storage ensures a consistent and environmentally friendly power supply. Unlike traditional diesel generators, HEBs operates with zero emissions. This is a significant advantage, especially for nuclear facilities where safety and environmental responsibility are paramount. By harnessing renewable energy sources, HEBs reduces our reliance on fossil fuels and minimizes the environmental impact of nuclear power generation. Efficiency is another hallmark of the HEBs system. It's designed to minimize energy loss during operation, making it highly efficient in converting and delivering power. This efficiency translates into cost savings and reduces the overall energy footprint of nuclear power plants. The elegance of HEBs lies in its simplicity and effectiveness. The reliability of HEBs is unparalleled. It operates independently of the grid, providing a constant and stable power supply regardless of external disruptions. This independence ensures the continuous operation of critical safety systems within the nuclear facility, preventing potential accidents and ensuring public safety. HEBs acts as an insurance policy, guaranteeing uninterrupted power when it matters most. Automation is key to the seamless operation of HEBs. The system utilizes the Profinet protocol, an industry standard for industrial communication. Profinet allows for real-time monitoring and control of all components within the HEBs network. This level of automation ensures optimal performance and swift response to changing conditions. Imagine a conductor leading an orchestra, ensuring each instrument plays in harmony. Profinet acts as that conductor for HEBs. It orchestrates the flow of energy, constantly monitoring and adjusting the system for peak efficiency and safety. This real-time communication is essential for maintaining the stability and reliability of the HEBs system. The Profinet protocol allows for predictive maintenance, identifying potential issues before they become problems. This proactive approach minimizes downtime and ensures the long-term reliability of the HEBs system. By analyzing data trends, Profinet can anticipate maintenance needs, preventing costly outages and ensuring the continued safety of the nuclear facility. Section 5. Out with the old, in with the new HEBs versus traditional systems. Traditional backup systems, primarily reliant on diesel generators, fall short in comparison to HEBs. Diesel generators are notorious for their slow startup times, often taking several minutes to reach full power. This delay can be critical in emergency situations where every second counts. Moreover, diesel generators produce harmful emissions, contributing to air pollution and environmental concerns. HEBs, on the other hand, offers an immediate response and clean energy, making it a superior choice for nuclear safety. The contrast is clear. HEBs represents a modern, efficient and environmentally responsible solution, while traditional systems lag behind. The stark difference between HEBs and traditional systems highlights the need for innovation in nuclear safety. The reliance on outdated technologies is no longer acceptable in a world demanding clean and dependable energy solutions. HEBs paves the way for a safer and more sustainable future for nuclear power. Section 6. Learning from the past. How HEBs could have changed history. History has taught us valuable lessons about the importance of reliable backup power in nuclear facilities. The need for dependable systems cannot be overstated, especially when dealing with something as potentially dangerous as nuclear energy. Incidents like the Fukushima disaster in Japan underscore the devastating consequences of power failures. The catastrophic event highlighted the vulnerabilities in our existing safety measures. The Fukushima Daiichi nuclear disaster, triggered by a tsunami, resulted in equipment failures and meltdowns. This tragic event serves as a stark reminder of the importance of having robust backup systems in place. The lack of a robust and independent backup power source exacerbated the situation, leading to a major nuclear incident. The failure of these systems had far-reaching consequences, affecting not just the immediate area but the entire world. HEBs, with its independent operation and quick response time, could have played a crucial role in mitigating the impact of such events. Its advanced technology ensures that power is restored almost instantaneously. By providing continuous power to critical safety systems, HEBs could have prevented or minimized the severity of these incidents. The system's reliability is its greatest strength. The lessons learned from past nuclear incidents emphasize the need for advanced backup systems like HEBs. These discussions are crucial for improving future safety measures. The integration of HEBs in nuclear facilities worldwide can serve as a preventive measure against future disasters. This global approach ensures a higher standard of safety. By learning from past mistakes and embracing modern safety solutions, we can work towards a future where nuclear energy is both safe and sustainable. The advancements in technology offer a promising path forward. HEBs represents a commitment to preventing history from repeating itself. It stands as a testament to our dedication to safety and innovation in the nuclear industry. Section 7. A hydrogen-powered future, the next step in HEBs evolution. Looking ahead, the future of HEBs is even brighter with the integration of hydrogen energy systems and solid oxide fuel cells, or SOFCs. These advanced technologies promise to revolutionize the way we think about energy storage and generation. Hydrogen, a clean and abundant energy carrier, can be produced from renewable sources and stored for extended periods. This versatility makes hydrogen an essential component in the quest for sustainable energy solutions. This makes it an ideal complement to the HEBs system, further enhancing its sustainability and resilience. By integrating hydrogen, we can ensure a more reliable and eco-friendly energy supply. SOFCs, known for their high efficiency and ability to operate on hydrogen, offer a promising technology for power generation within the HEBs framework. These cells can convert hydrogen into electricity with remarkable efficiency. These fuel cells produce electricity with zero emissions, aligning perfectly with the clean energy goals of HEBs. Zero-emission power generation is crucial for reducing our carbon footprint. The combination of hydrogen and SOFCs represents a significant leap forward in backup power technology for nuclear facilities. This integration ensures that nuclear plants can operate safely and efficiently, even during unexpected outages. Imagine a future where nuclear power plants are not only safe, but also contribute to a cleaner environment. This vision is becoming a reality as we continue to innovate and integrate green technologies. This vision is within reach with the continued development and integration of hydrogen energy and SOFCs into the HEBs system. The ongoing advancements in these fields are paving the way for a more sustainable energy future. It's a future where nuclear energy can play a vital role in a sustainable energy mix. By combining nuclear power with renewable hydrogen and efficient SOFCs, we can achieve a cleaner, more resilient energy landscape. To Section 8, HEBs, a beacon of safety and sustainability for nuclear energy. In conclusion, the Hybrid Electrical Energy Backup System, or HEBs, is revolutionizing nuclear safety and sustainability. By seamlessly integrating renewable energy sources, advanced automation, and cutting-edge technologies like hydrogen and SOFCs, HEBs offers unparalleled reliability, efficiency, and environmental responsibility. The adoption of HEBs is not merely an upgrade, but a fundamental shift towards a safer and more sustainable future for nuclear power. As we move towards a world increasingly reliant on clean energy solutions, HEBs stands as a beacon of innovation, setting new safety standards for the nuclear industry and paving the way for a brighter and more secure energy future. The implementation of HEBs is an investment in the future, ensuring that nuclear energy can continue to power our world without compromising the safety of our planet or future generations. It's a testament to human ingenuity and our ability to harness technology for the greater good. HEBs not only enhances the safety protocols, but also ensures that the energy produced is cleaner and more efficient. This system is a game changer, setting a new benchmark in the nuclear energy sector. By adopting HEBs, we are taking a significant step towards a future where energy is not only abundant, but also safe and sustainable for everyone.
We use energy every day. From the moment we wake up and switch on the lights to the time we go to bed with our phones charging beside us, energy is a constant companion in our lives. Lights, phones, cars, they all need power. Our modern lifestyle is built on a foundation of reliable energy. But what happens when the sun goes down or the wind stops blowing? The challenge of intermittent energy sources becomes apparent. That's where energy storage comes in. These systems are designed to store energy when it's abundant and release it when it's scarce. Think of it like a battery for your house or even your whole city. These storage solutions can power homes, businesses, and entire communities. Renewable energy sources like solar and wind are great, but they're not always available. The sun doesn't always shine, and the wind doesn't always blow. That's where energy storage technologies come in. They bridge the gap between energy supply and demand, ensuring a steady flow of power. They capture energy when it's plentiful and save it for when we need it most. This not only provides reliability, but also enhances the efficiency of renewable energy systems. It's like having a savings account for energy. By storing energy, we can save money on energy bills and reduce our carbon footprint. In this essay, we'll explore the fascinating world of energy storage, focusing on different technologies and their applications. From household batteries to large-scale storage facilities, the possibilities are vast. We'll delve into the workings of lithium-ion batteries and supercapacitors, understanding how they store and release energy. We'll compare their strengths and weaknesses and discuss safety considerations. Each technology has its own set of advantages and challenges. We'll also examine emerging technologies like SMES and HES, which offer new ways to store energy more efficiently and effectively. These cutting-edge solutions have the potential to revolutionize how we store energy, making our power systems more resilient and sustainable. Get ready for an electrifying journey into the future of energy. Together, we'll uncover the innovations that are shaping a more sustainable and energy-efficient world.
You're probably familiar with batteries. They're in your phone, laptop, and maybe even your car. These are often lithium-ion batteries. They're great at storing lots of energy in a small package. Lithium-ion batteries work by moving tiny particles called ions between two electrodes. When you charge the battery, lithium ions move from one electrode to the other, storing energy. When you use the battery, the ions flow back, releasing the stored energy. These batteries are popular because they're rechargeable, have a long lifespan, and can store a lot of energy for their size. But they can also be sensitive to temperature and can degrade over time. Inside, there's a separator that keeps the electrodes from touching, which is crucial for safety. Modern devices use battery management systems to monitor and protect the battery. These systems help prevent overheating and overcharging, extending the battery's life. As technology advances, batteries are becoming even more efficient and powerful. Researchers are constantly working on new materials and designs to make batteries safer and more efficient. The future of batteries is not just in electronics, but also in renewable energy storage. Home battery systems and smart grids are becoming more common, helping to store energy from renewable sources like solar and wind. Electric vehicles are also benefiting from advancements in battery technology, making them more practical and efficient. And let's not forget about recycling. Properly recycling batteries can recover valuable materials and reduce environmental impact. So next time you use a device, remember the small package that's powering it and the big energy it holds. Supercapacitors are like the sprinters of the energy storage world. They are designed to deliver energy in quick, powerful bursts, making them incredibly efficient for specific applications. They can charge and discharge energy incredibly fast, much faster than traditional batteries. This rapid energy transfer is what sets them apart and makes them so valuable in modern technology. This makes them perfect for applications that need quick bursts of power, such as electric vehicles that require rapid acceleration, industrial machines that need to start up instantly, and high-performance electronics that demand immediate energy. Instead of storing energy chemically like batteries, supercapacitors store energy electrostatically. This fundamental difference in energy storage method gives them unique advantages. Imagine it like static electricity, but much more powerful. This electrostatic storage allows for quick energy release, which is crucial for many high-demand applications. This allows them to charge and discharge quickly without wearing out as fast as batteries. Their longevity and efficiency make them a reliable choice for repeated use. Supercapacitors are used in hybrid vehicles for regenerative braking, capturing energy when you brake and releasing it for acceleration. This process not only improves energy efficiency, but also enhances the performance of the vehicle. They're also used in electronics to provide backup power, ensuring that devices remain operational during power interruptions. This is especially important for critical systems that cannot afford downtime, and in industrial equipment for short bursts of high power. These bursts are essential for machinery that requires a lot of energy in a short amount of time, ensuring smooth and efficient operation.
Storing energy safely is crucial. Whether it's a battery in your phone or a giant energy storage system, safety is paramount. We need to be mindful of potential hazards and take precautions. Lithium-ion batteries, while generally safe, can pose a fire risk if damaged or overcharged. That's why it's important to use them properly and dispose of them responsibly. Always follow the manufacturer's instructions. Supercapacitors, while generally safer than batteries in terms of fire risk, operate at high voltages, which can be dangerous if not handled properly. Proper insulation and safety protocols are essential when working with supercapacitors.
Scientists are always working on new and improved battery technologies. They're exploring new materials and chemistries to create batteries that are safer, more efficient, and longer lasting. One promising area of research is solid-state batteries. These batteries replace the flammable liquid electrolyte found in lithium-ion batteries with a solid electrolyte, potentially making them safer and more energy-dense. Another area of research is using different materials for the electrodes, such as silicon or lithium metal. These materials could potentially store much more energy than current lithium-ion batteries.
Superconducting magnetic energy storage, or SMES, is a fascinating technology that stores energy in a magnetic field created by flowing electricity through a superconducting coil. It's like having a giant electromagnet that stores energy. SMES systems can store and release vast amounts of energy very quickly, making them suitable for grid-scale applications, such as stabilizing power grids and supporting renewable energy sources. While SMES is highly efficient and has a long lifespan, it requires cryogenic temperatures to maintain superconductivity, which can be expensive. Research is ongoing to develop high-temperature superconductors that could make SMES more practical.
Hydrogen energy storage systems, or HES, use hydrogen as a fuel to store and release energy. Excess electricity from sources like solar or wind power is used to split water into hydrogen and oxygen through a process called electrolysis. The hydrogen can be stored in tanks and later used in fuel cells to generate electricity on demand, with only water vapor as a byproduct. This makes HES a clean and efficient way to store energy. HES is well suited for long-duration energy storage, potentially providing grid stability and supporting the transition to renewable energy. However, challenges remain in terms of hydrogen storage, transportation, and infrastructure development.
Managing energy storage systems, especially on a large scale, requires sophisticated control systems. This is where automation comes in. Automation networks act as the brains behind energy storage, optimizing performance and ensuring safety. These networks monitor and control various parameters, such as charging and discharging rates, temperature and voltage, ensuring the system operates within safe and efficient limits. Automation plays a vital role in integrating energy storage with renewable energy sources, allowing for seamless transition between different power sources and ensuring grid stability.
Nuclear power plants generate electricity consistently, unlike intermittent renewable sources. Integrating energy storage with nuclear power can enhance their flexibility and reliability. For instance, excess electricity generated during periods of low demand can be stored and used later during peak demand periods. This can help smooth out fluctuations in electricity supply and demand, improving grid stability. Moreover, energy storage can enhance the safety and efficiency of nuclear power plants by providing backup power during emergencies and enabling more flexible operation. Energy storage is essential for a sustainable energy future. As we transition to more renewable energy sources like solar and wind power, we need efficient and reliable ways to store the energy they generate. From batteries in our devices to grid-scale storage systems, these technologies are key to unlocking a future powered by clean, reliable energy. As technology advances and costs decrease, energy storage will play an increasingly important role in our lives, powering our homes, businesses, and transportation systems. The future of energy storage is bright, and it's an exciting time to be part of this technological revolution.
As we wrap up, I would like to extend our deepest gratitude to Associate Professor Dr. Ashraf Aboshosha from the Radiation Engineering Department, Industrial Irradiation Division, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority in Cairo, Egypt, for his remarkable efforts in conducting such an innovative and insightful study. His dedication to advancing the field of radiation engineering is truly commendable, and his work has the potential to make significant contributions to both the scientific community and society at large. His research, titled Automation Network Computer-Aided Design of Hybrid Electrical Energy Backup System for Nuclear Microgrids, published in the International Journal of Hydrogen Energy, Issue 90, 2024, is a testament to his dedication and expertise in this critical field. This groundbreaking study explores the integration of hybrid electrical energy systems within nuclear microgrids, aiming to enhance their efficiency and reliability. By leveraging advanced computer-aided design techniques, Dr. Aboshosha's work provides a comprehensive framework for optimizing energy backup systems, which is crucial for the stability and sustainability of nuclear power infrastructures. We also want to thank you, our valued audience, for continuing to support the For Science Salah Lotfy channel. Your enthusiasm and curiosity drive us to bring you the latest and most impactful scientific discoveries from around the world. Without your support, our mission to disseminate knowledge and foster a deeper understanding of science would not be possible. Your engagement helps us bring these important scientific breakthroughs to a wider audience. By liking, sharing, and discussing our content, you play a vital role in spreading awareness about the incredible advancements being made in various scientific fields. Together, we can inspire future generations of scientists and researchers to pursue their passions and contribute to the ever-evolving landscape of science and technology. Stay tuned for more exciting research, and as always, thank you for watching. We have many more fascinating topics lined up, and we can't wait to share them with you. Remember to subscribe to our channel and hit the notification bell so you never miss an update. Your continued support means the world to us, and we look forward to embarking on this scientific journey together. Thank you, and see you next time.